today I will talk to you about functional patterns that you can use in Scala, and it's oriented toward like beginners in Scala for a simple reason. Like when I learned Scala, I came from Haskell, and it was okay because I knew all the stuff from Haskell, and I was just able to port it in Scala. But when you started functional programming in Scala, you're somehow expected to know all the functional patterns from Haskell. And it's a bit a shame that you're forced to learn a new language to be efficient in Scala. Okay, quickly, if you have questions or stuff to say, don't hesitate to put that on Twitter, so I will be able to answer afterwards, and people not in the room will be able to discuss it. I have also a blog if you're interested in that. Just quickly, I'm working for a company called Cloud. It's a platform as a service, so you git push your code, and we handle everything for the operations, like restarting and failure, stuff like that. And our second core business is giving away awesome stickers, so if you want stickers, just ask me. Okay, so yeah, in my day-to-day life, I'm a functional programmer. I'm also serve as a CTO of the company, but I started as a functional programmer. Basically, my two main languages are Scala and JS. I try to program in a functional style in both. It's a bit harder in JS because there is less tooling, but yeah. Writing functional code is not really a matter of language. It's just a matter of how you think about your code and stuff like that. Okay, so just to make sure everybody's awake, since the party was funny yesterday, a very simple functional pattern just to get warmed up. It's a zygo-isomorphic prepomorphism. Should be okay for everyone, unless you want a generalized zygomorphism. Whatever that means. No, more seriously, oh yeah, or not. I won't talk about functional abstractions today, like functors or monads, stuff like that. I will talk about how we encode it in Scala, and the tools we rely on to encode that. So the idea is that when you know these basic tools, you're able to understand how this abstraction works, and then you're able to read about it, even if it's explained in Haskell or in another language. Since you know it's encoded in Scala, you can understand what's going on. Also, there are different ways. Since these patterns are not encoded at the language level in Scala, there are different ways to encode them. I will show you one, hopefully the simplest. There are better ways to do that, but it depends on what you really want to do and stuff like that. So I will show you every time one way to do that. Keep in mind that's not the only way. That's the beauty of Scala. Okay, just to start with Scala, and like it's both object and functional programming. And our object-oriented nature of Scala is quite well documented, since it's encoded in the language. If you read a book about the language, you will learn about like traits, stuff like that. It's well documented. FP patterns, on the other hand, are not that well documented because, for instance, Scala Z, it somehow expects you to learn to know Haskell, or there have been great pieces about using Scala Z, but it's always like we're taking this Haskell idiom and port it to Scala, so it's not always easy for beginners. And yeah, I will focus on patterns. They are not intrinsically functional, but they are common in functional approaches. Object orientation will play a part in implementing them, but not in just more implementation, not really design. Okay, so the first question, and which has no definite answer, is what is FP? There are many definitions. Some say it's programming with functions, stuff like that. A definition I really like is you program with values. Like all your data flow or your control flow is encoded as values, and that's how your program runs. which is nice because it's easy to follow the flow of the program. And a core thing for that is that almost everything or everything is an expression, which is the single most important thing to know when you're programming functionally, is that think in terms of expressions and how they relate to each other. For instance, if block is not just control flow, it's an expression returning a value. And that's especially good in a statically typed language, because since your control flow blocks become expressions, then there are values, and then you're able to use the type system to check your control flow, which gives a much more power to your type system. So if, I think everybody's okay with that. Also, you can deconstruct stuff, so it should be okay. Everybody has like a working Scala knowledge, or yeah, should have asked before. Sorry. And yeah. So as I said, since the control flow is encoded as values, and you're able to type check your control flow, and that's very, very nice. And it enables something called algebraic design, which is a fancy word for domain-driven design with functional tools, basically. Like just observing your problem and encoding how it works and properties, stuff like that, into your code. But instead of using object-oriented tools, you can use functional tools. So the first thing is, how do we model data in this sense? We're not like using huge subtyping hierarchies and stuff like that. So what's commonly used in functional languages is something called algebraic data types, which has a word in common with algebraic design, but it's not exactly the same. So basically, to sum up, and it's not like theoretically perfect, but bear with me. An algebraic data type is comprised of two things, things like product type and sum types. Product types, I think you already know that. It's tuples or case classes, stuff like that. It's like a Cartesian product. You're putting a value of one type and a value of another type, you're putting them together. And if you think about it in set theory, it's like a Cartesian product. So to create it, I just put two or more values together, either in a tuple or in a case class. So that's just it. A product type is just putting several values together, nothing more. And you can also eliminate it. Since we know we always have these values, we can deconstruct it directly at when assigning variables. You're not forced to do that in a match block. But yeah, basically it's a way of like mashing values together. Quite simple. And we call it product because if you think about the numbers of different values, if you think as types as sets, then it's a product. So the number of elements, like the cardinality, is a product of the cardinality of the individual types. For instance, if I have a tuple of 2 Boolean values, the cardinality of Booleans is 2, and 2 times 2 equals 4. So that's why it's called product, amongst other reasons. The other hand, it's called a sum type, which is harder to find in mainstream languages, and it's not directly provided in Scala. It's called sum types or disjointed union, stuff like that. I think an example that everybody already knows is JSON. You've got several types of JSON values, and you know that either you have this or you don't have anything, but nobody can come up with a new JSON value or a new kind of JSON value. It's this choice and nothing more. So that's why they are so close, called closed unions. And you can't really express that in an object-oriented language with subtyping because it's open. Like if you want to have subtypes of one interface or one class, then everybody can subtype it. So in Haskell, you got direct encoding in the language with the pipe saying or. In Scala, there is not direct syntactic support for that. So we're using object orientation and subtyping, but with an important different thing is called sealed. So I define a trait, thing should be okay for everyone, and then I have case classes or case objects extending this trait. And the important part is just the seal keyword. A seal trait is a trait that nobody can extend outside from the file it was defined in. So the sealed keyword gives you the closedness of your type, which is good because if you have a value of type JSON-LM, you're sure that it's one of these alternatives and not another one, and you are sure, and the compiler is able to statically verify that. And to work with that, the simplest way is to do pattern matching. So it will allow you to describe what to do in each case, and it will allow you to access the values inside stuff, so deconstructing. For instance, this is a function that stringifies a JSON object, or a JSON value anyway. Okay, and yeah, since we have a seal trait, the compiler is able to tell you if you are forgetting a case. Like in this case, I forgot to handle the case for a JSON string, and the compiler is able to tell me that. And since it's not encoded directly in Scala, we do it kind of manually. There are differences in Scala and other language which have direct support for that. Sometimes it's a problem, sometimes it's nice. For instance, with JSON, of course the JSON values, it's either string, a boolean, stuff like that. But if you're expecting a whole JSON object, it's either an object or an array. You can't. A JSON string by itself is not correct. It has to be in an array and an object, stuff like that. So if I define a new seal trait called JSON value, and I just have to make JSON array and object extend it, and then without repeating the tree or the ADT, I'm able to tag a few cases with a new trait, which is like hard to do in Haskell, for instance. So it's not always a good thing, but it has definitely had more flexibility. Another thing is that since we have case classes, every case has its own type. So if you want to have a function that operates only on JSON arrays, you're able to do that. In Haskell, for instance, you can do that. You're forced to wrap it into another level of types. It's not always practical, especially because of type inference. And it's not like a sum type. Alternatives should not be types in themselves. But that's how it works in Scala, and frankly, it comes in handy from time to time. So know that is a difference between like a real algebraic data type and how we encode it in Scala. But these differences are not always a problem, and sometimes it's very good. Okay, so just to sum up, in OOP for that we would have method on classes, and we would let the dispatch to the class hierarchy. With ADT, it's pattern matching. So it's a different solution to the same problem. And which means in OOP, it's easy to add cases because you just drop a new class, you extend your interface, and you implement all the necessary methods. So you can do that in isolation. You just drop in a new file, and that's okay. In FP, it's the contrary. if you want to add a new case, you're forced to go to every pattern match and add a new case. On the other hand, it's easier to add function. Like, you just create a new function, you pattern match, and that's all. So yeah, this stuff, it's called like it's an avatar of something called the expression problem. So if you want to learn more about it, it's quite interesting. But that's one thing you have to be aware of, is that syncing with ADTs is in some cases better because you got closure, stuff like that. But in some cases, it's more complicated than just working with a subtyping hierarchy and inheritance. Okay. Another thing is that you can use generic types like tuples and either and stuff like that to encode your generic your ADTs, or you can enroll your own. I don't have like a rule of thumb for that. It's like use your best judgment. I usually prefer to have explicit types and stuff like that, even though they're isomorphic, but I prefer to be like explicit about it. For instance, a tuple of string and int is isomorphic to a case class with string and int as field. When I say isomorphic, I mean I'm able to construct a pair of functions transforming one into the other, and like they have the same structure, basically. And that's the same with some types. You can do everything with either if you really want to, but if you start to have like 3 levels of eithers imbricated, maybe you should write your own ADT, your own sum type. Who knows? And I'm coming back to the like sum and product name because they behave in many ways exactly like addition and multiplication, and it gives rise to fun equivalences, and it's useful when you're designing your data types. For instance, we all know that if you multiply by 1, then you get the same value, and the same with if you add 0 to a number. And like a bit more complicated, but multiplication and addition are associative, and multiplication distributes over addition, and yeah, stuff like that. And also, I will go one by one. And if you have exponentials, then addition turns into multiplication. So you've ever seen that? The pair of empty parentheses called unit. It's called unit for a simple reason. It's because it has the same structure as 1 with respect to multiplication. It's a type that has only one meaningful value, so it's a unit type. And it looks like an empty tuple, because if you got a product of nothing, it's equal to 1. And a tuple of nothing is a product of nothing. So it's the equivalent of the number 1 in terms of types. And this one is not implemented directly in Scala, but it's a type that has 0 inhabitants. So it's a type that doesn't have any value, so it can't compile. Okay, so if you multiply a by 1, you get a. So a tuple with a and unit gives you a, which should be okay. If you add 0 to a, it means like either you got a value of type a, or you got a value that can be constructed. So it's basically a value of type a. You are not able to construct a value of type void. And for associativity of tuples, it means like you can nest tuples arbitrarily. It will be the same as like a flattened out tuple. So these tuples are equivalent. So it just means that you can like flatten out stuff, and imbrication is useful for you, but structurally it can go away. And it's the same like for case classes or tuples, stuff like that. And the same property holds for addition, of course. It means like you can encode everything with any sum type with either, since This is equivalent to that. A flat sum type is equivalent to an imbrication of pairwise sum types. So either you do that with imbricated ithers, or you define your own sum type, and it's like arguably simpler. Okay, and also, yeah, distributivity. It's a bit funnier. The two things are equivalent. Either I have a tuple of a value and sum type, or I can move the sum type at the top level. In that case, the first value. In the first case, the first value is factored out, and it's like literally factoring out code, which is nice. And yeah, if you add x n times, it's n times x, and it means that if you have several cases in a sum type with the same structure, then you can factor it out with this structure tuple with an nm. Okay, so we get two cases, both with a string. So it's equivalent to a product type of a string and an nm, stuff like that. And next thing is like, basically it's a case analysis. Functions are equivalent to exponential types. So C times A plus B, it means a function from A or B to C. And it's equivalent to a tuple of function for each alternative, which is what you do when you're writing a fold or doing case analysis in a pattern match block, stuff like that. So yeah, since I'm talking about it, please avoid booleans. You can make your own enums. There will be isomorphics that will have the same structure, but it will be explicit. Booleans can come from anywhere. Your own enum, it's your own enum, and you are forced to construct it explicitly. A bool can come from anywhere, so it's not as good. Okay, going back to programming with values. What I mean is not just having string and stuff like that. It's putting back much more abstract things in the realm of values, and you're able to put context in the value, like this operation has failed, or this operation is non-deterministic, stuff like that, which is very abstract. You're able to put that into the value and get back your type safety goodness, stuff like that. A good example for that is error handling, where in Java it's like a mix of checked and unchecked exceptions. In Scala you've got exceptions too, and the simplest way to put it into the realm of values is an option. Like, if it has failed, then you get a none. If it has succeeded, you get a sum, and that's all. Of course, it's not very useful if you're interested in the actual error, but that's the first step in getting back context in your values. Or in Haskell, you can call it maybe. But yeah, only use it when only one thing can go wrong, because either you're just losing information, and losing information is bad. If you want to retain information in Scala, you got something called either. Either you got a left or a right. By convention, right contains the value that you are expecting, and left contains the error, if you have an error. When working with that, the fact that either is polymorphic on the error type, unlike try, which forces you into having a throwable stuff, with either you're able to use an ADT to encode the error, which is very, very good, because you're keeping structure information. Either string something, that's code smell, really. So when you're designing your code, you know the different kinds of errors that can happen, and you can do that Yeah, that should be case objects, sorry. But you can like retain this information, and since it's an ADT, you're able to deconstruct it with pattern matching, and you're able to see if that you've forgotten to handle a case. If you got a string, then you're losing all structure and whatever. It's bad because you construct strings with a structure in mind, and then you just throw away the information you had. With ADTs as error types, you're able to retain this information. So in this case, you just have the happy path with the right, and for the left, you're able to enumerate all the possibility of errors, and then you're forced to be exhaustive when handling errors. Okay, so that's good. Keep in mind that by convention, right is the happy path and left is the error path. But that's just a convention because either provided by Scala standard library is not biased. So if you want to use a flat map and stuff like that, you're forced to, at each step, say to Scala, I'm interested really in the right. So if you want to like chain either values, don't forget to put the dot right at the end when you're calling flat map or writing a for block. So how does it work is that since as long as it's right, it's okay, and it will fail at the first left. So the first left is B, and we've got operation to fail. Okay, so it's a bit like exceptions. Like at the first problem, it just stops and you're just there. There are other issues with either, since every case has its own type, that's how you encode ADTs in Scala, you got inference issues because there is no unification across queried arguments, if I'm not saying a mistake. But simple case, you're doing a fold on something, and the base case is an empty list or a left or stuff like that. And then it will infer that it needs a left, and it won't be able to unify between left and right and find that what you really want is an either, not a left or right. So that's a common problem when working with either. And another thing is that sometimes you will see product reserializable with Scala.util.either. Just a signature of several functions in the standard library. It's not a problem in itself, but yeah, it doesn't feel right. So for this, you can consider using Scala Z or Scala Z disjunction. Yeah, the backward forward slash is pronounced disjunction. It's biased to the right, so it's expecting you to put happy path in the right, okay? And you get constructors with proper type annotation, which won't cause any problem of type inference. Like disjunction.right, it will return a value of type disjunction and not just a value of type forward backslash forward slash dash, which is constructor. And it works exactly the same way as either does. It's like just right biased and failing fast. And failing fast, that can be an issue. If your error is like stop the world errors, that's okay. But sometimes it's not what you want. A regular example is that you're filling out a long form with like it's asking you twice your address and stuff like that, and your mother's maiden name, whatever, and it validates the field one by one, and you've got to refresh the page every time to learn the new error, and you really feel that like the guy or the programmer who wrote that is just trolling you. So sometimes what you want to do is like explore every alternative in parallel and accumulate errors. And for that, there is something called validation in Scala Z. So you could like value.success null or error.fail null, and it will return you a value of type validation null, which will act the same in a sense in the same way as either, like either you got your value or not. I will go back to the null just now. Null means non-empty list. Is that like you're accumulating errors? So instead of accumulating them in a list, where the empty list, it means I got an error, but I don't have any error. It doesn't make any sense. So you're using a non-empty list to make sure you've at least one error. So like this kind of error message can be just suppressed if you're using non-empty list. And then you got your individual validation functions, and you combine them with something called the burn operator or the home alone operator on the munch cry operator. It has several names, but it's just pipe, @pipe. Sorry. We like symbols in Scala. But what it does is that it combines the validation function and accumulates the error if there are errors. So either I got a success of my user, or I got a failure containing a list of errors, and which is nice because it will accumulate errors. So keep in mind that sometimes you want error accumulation and sometimes you don't want that, and those two types actually encode it in the type. So when you're looking at the type, you know that if this fails, it fails beyond recovery, so it will stop everything if you got a disjunction. And if you got validation, it says everything can be tried out in parallel. I just want the accumulation of errors. So it's encoded in the type how you want to work with errors. Also, another thing I've learned is that you don't always want to flatten errors, like having just one level of errors. Sometimes you want a level of errors like related to the user input, but if there is a problem with the database, stuff like that, you may not want to mash them user input errors and critical errors like the database is not responding. So maybe you can have like an either of validation or either of either. It can make sense. And sometimes you got errors like are critical and beyond recovery, so you need an either. And the rest of the error is just accumulatable errors, so you will mix either and validation. And that's not a problem. Okay, so next up, how do we do extensibility in a functional setting? Like we're not using inheritance and stuff like that. So there is a solution invented in Haskell and used in other languages now, which was defined in a paper called Ad-Hoc polymorphism, but little less ad-hoc. We'll start with a simple example, which is called a monoid. And you should be interested in monoid if you're interested in big data. Basically, monoid allow you to distribute computation over several nodes, and knowing that the end result will be the same whichever way you distribute it. So a monoid is just a matter of combining two values with associativity, which means like if you got a huge chain of operations, you can do intermediate operations in any order you want. You've got the property that the end result will always be the same, which is why it's so interesting when you want to go parallel. And it has a neutral element with left and right identity, so it's like a no-op. A first object-oriented try would be to define a trait monoid with an operation combine, which would take another monoid and return a monoid. And then, yeah, let your types extend it. But it has like a lot of problems. First of one is you're losing information. Like you're saying, I want a monoid, but you're losing the actual type. Since it's you extend it, you can't extend final classes, so you can't have first class support for native types, for instance, And how do you encode 0? Because 0 is not related to a monoid instance. It just exists for a monoid. So a solution would be an external declaration, because it would solve a lot of things. So how we do? We define a trait, which won't be extended by the type itself. It will just hold the operations. So we got the M0, and the append operation takes 2 values of type A. It's parametric in A, so we don't lose any information about the actual type. We just know that A has to be a monoid, and the 2 values have to be of the same type. And since it's external, you can implement it for native types or regular types or your types or whatever. It's not a problem. Okay, so I will just repeat that. You can't use it for finite types. You don't lose information, and you can encode 0. And to implement that, you create a new instance. Like string behaves as a monoid. Append is like string concatenation, and 0 is the empty string. So you create a new instance of monoid of string, and you put stuff there. And then, if you want to use it, you can pass it as an extra argument to function who rely on the monoid properties. Like for instance, concat takes a sequence of values, monoidal values, and reduce it to 1 value. Like it can be like a sum, a product, or MK string, stuff like that. So I just have to pass a good instance every time, and the type system will check that. But it's a bit tedious, so what we really want to do is to have it automatically wired. And every time you have a problem in Scala, the solution is implicit, yeah. Like if your compilation is too quick, just drop in some implicit and it will slow down nicely. So when you're defining your instance, you just drop an implicit keyword before it, and when you ask for a monoid behavior on your type A, you just put an implicit. And then, this way. Another way, which I find quite elegant, is that basically it means the same, that in the when you say that your function is parametric in A, you want to be an implicit instance of monoid of A in scope. And then you get the instance by calling implicitly. So it's the same. In this case, you're using implicitly to get the instance, but that's the same thing. And for use, then you get the code without having to manually pass the instance. And yeah, integers behave as monoids in many different ways. So using implicits, it kind of forces you to have only one behavior for each type, which is called type class. Don't mind the E, I'm French. Convergence, which means that it's generally a good idea to have only one instance of a type class for a given type. So in Scala Z, for instance, it's like mandatory to do that. So you're forced to wrap types to explicitly declare the behavior. It's an ongoing debate. Scala allows you to provide your own instance if you want to, so you can use multiple instances for same implementation. It's generally frowned upon in the Scala Z community. In the rest of the Scala community, it depends on who you're talking to. Okay. Another place where type classes are used a lot, it's serialization. You know shapeless? It's like type astronauty things. It's very nice. And one day, Miles Sabin tried to use Spark with shapeless values, and he found out that Spark relied on Java serialization. So every time I had to extend serializable. And that's sad. Like, there is a huge commit in Shapeless where he basically had serializable everywhere. And you can feel the pain in that commit, and it's everywhere. And for serialization, type classes are very, very good. Like, let's say we want to transform a value into JSON. We create a type class called toJSON, parameterized in A, which has only one function, transforming an A into a JSON element. And then, for our own values of A, like if you're on types, then you provide the implementation. And what's very, very, very nice is like the types provided by Scala, like a map. It's a map of string to something. It's easy to turn into a JSON object, provided the something is turnable into JSON. So with the type class mechanism, the implementation made for default type in Scala will be able to pull implementation for your own types. So there will be no boundary or no like impedance mismatch between types natively or directly supported by the library and type you implement yourselves, which is very, very nice. And if you've used Play Framework, it's central to its design, and it's one of the reasons I like Play. So JSON is done like that. DB objects, if you use ANORM, which is like an old thing, but anyway. You implement type classes for reading and writing to database. Query string parameters, like if you want your user to give you a UUID in the query string or a datetime, stuff like that, you just have to describe how to parse and to transform this object into strings, and then it's used directly from the routing framework of Play, and it's like it feels natural. And you also can do forms. Once you understand the concept of type classes, then you're able to read parts of the Scala Z code, or Scala Z, whatever. Scala Z is like constructed on top of type classes, so it's really the main thing to know about when reading Scala Z. And then you're able to read the code, and you're able to find new abstractions you didn't know you needed, stuff like that. Okay. Another thing with type classes, which I haven't mentioned, is that type classes should come with laws. Like a monoid, it comes with associativity and left and right identity laws, and they are very important. And a good way to assess for these laws is to use something called property-based test. Regular unit tests, it just proves the presence of bug, not the absence. Like I'm legally forced to cite tags around that. And the types, it's exhaustive and it's for all. The good thing with property-based tests is that they give you the same reasoning of types, like property-based and for all-ish, but at the value level. And of course, it's not exhaustive, but it's like a nice inversion of control. In Scala, you got something called Scala check. Quickly, it provides you with the values, you compute operation in it, and then you check properties on the result. So it's not your responsibility to provide the test values, and that's how you're able to find bugs easily. And when it comes to laws of type classes, the law of monoid, for instance, it says like for all A append 0 is equal to A, and it's exactly the same way of reasoning. Okay, and the next one, or the last one actually, it's a bit more work, but if you can do that, it's very nice. The idea is to separate the decision-making code and the effect-taking code. You keep a pure core, which is only like logic, and it takes decision, but it doesn't act on them. And then the effects, you try to encode them as an ADT and push them. So, for instance, you could have like an add user case class saying, provided you have this user, please insert it in the database. Or instead of just moving money around, you issue an instance of transfer amount, and give the two users and the money. So in one part of the code, you just declare that what you want your system to do, like insert that, stuff like that. And then you push back the interpretation, what we usually call at the end of the world. So to keep like a mostly pure core and pushing side effects or effects at the boundary of this core. Will ask me, but why? Like, it feels complicated. Why can't I just ask or like push that in the DB? The main point for me is that it's easier to test. If you want to assess that your code decides to write to push the user in the database, if you mix a decision with effects, then you're forced to write mocks for a database, and it gets untidy very quickly. And it also brings you flexibility, because you're able to act on the effects before they're affected upon. So you can deduplicate effects, you can merge them, or you can do everything you want. And if you persist the effect description, you can even go back in time, undo something, or have your system behave as some effects didn't happen, stuff like that. So it's basically why event sourcing is good and stuff like that, but you can also have it in your code. Event sourcing is like at the architectural level, but you can have it at the code level as well, thanks to that. Okay, so just to recap, use ADTs and enums to model your data. It's good because it's closed. Nobody can like add new cases from the outside. Materialize your errors in types. Because since Scala only has unchecked exceptions, you're not able to really check for them. And encoding errors as ADTs is a good thing. That's a big problem with Scala's try, is that since everything is throwable, you're not allowed, you can't inspect the actual error easily. If it's an either or stuff like that with an ADT, then it's very easy to deconstruct and act on the error. Yeah, for modularity, type classes, that's very, very good, especially for things like serialization. It's honestly like unbelievable that it's not more used. Then what you can't check by types, check them by property-based tests, and it's very effective. And the last step is like try to segregate effects. It's not easy to do, and it comes project after project, but at some point it's very, very nice to have that, and your code base will be much simpler for that. So one book to read is FP in Scala. It's a red book written by Runa Bjarnason and Paul Ciusano. It's a very, very good book, very comprehensive, very easy to follow. So if you want to read one book about being functional in Scala, it's this one. Thank you for your attention. If you like my gifts, they're here. And if, yeah, it's a pipeline made with Haskell and Amazon S3 and stuff. It's very like hipstery. And if you want to try Clever Cloud, there is a coupon, extraordinary 15 obviously, which will give you like 15 euros to test Clever Cloud. Thank you. And I think we have 2 minutes for questions. Yeah. The name of the book is Functional Programming in Scala, written by Runa Bjarnason and Paul Ciusano. It's edited by Mannings, and it's a red book, and it's a good book. Okay. No more questions? Yeah. Yeah. Okay. Yeah, it means if you've imbricated tuples, you can flatten them into one big tuple.
Okay, so
That's for some types. Is that the same thing? You can imbricate eithers. It's because it's a sum type and it's associative. And the example is with either because either is already provided by the Scala standard library. So that's an example. It means like you can encode any ADT with tuples and either. Thanks.